Okay, welcome to Analysis 1A, lecture number 6. Students had a quiz at the end of last class. They got it back. It's a big secret. No one sent me a check in the mail, so I did not grade your quizzes, internet. And we have moved on, and we just went over it. Actually, everyone, can you erase the backboard when you get a chance? Yeah. So today we're going to do some learning, and we are going to start with going over Limits Review 3. And Limits Review is the last of our limits worksheets. I passed this out. Actually, I forgot to give it to you guys, right? Is that what happened? Yeah. I'm a terrible teacher. I tracked some of you down, and the rest of you just had to print it on the internet. I apologize for that. Anyway, let's go over this. I thought most of these were kind of easy, so I don't think we need to dwell on this, but students put all the prompts up on the board. Let's check it out. Number 1, try to plug in 2 is a 0 over 0 situation. So you tried some algebra, you go back, factor, boom, boom, difference of cubes, and the correct answer is 3. Here we are taking the limit as x goes to infinity of 1 over 3 to the negative x, which is just 3 to the x. That is definitely true. And so 3 to the x just goes to infinity as x goes to infinity, of course. We're taking the limit as x to infinity of sine squared. This person drew a little generic kind of squiggly, which is actually pretty accurate, except there's no scale, so we can't really be sure. And the answer is does not exist. I very much agree. In fact, just a little comment that we can make about this, and because this is the kind of thing I expected you to know, there's a formula for sine squared x, which comes from the cosine 2x formula. What is the cosine 2x formula, which involves sine squared? 1 minus 2 sine squared. Do we agree with that? Yeah, that's right. So since that is the formula for cosine 2x, it is possible to actually solve for sine squared. What is sine squared?
1 minus cosine 2x over 2.
Yup, by the power of algebra, this is 1 minus cosine 2x over 2. So that's just an important formula in its own right. It is the so-called power-reducing formula. It's the formula which enables you to take the square of a sine function and just convert it to a trig function with a linear power. So that's an important formula that you do need to know. It comes up sometimes. That's kind of nice because it tells me that this is not just some generic squiggly, but is in fact 1/2 minus 1/2 cosine 2x. And so actually I know exactly what this function looks like. It has been moved up by a half. It has amplitude 1/2, looking pretty good. It is otherwise an upside down cosine, which is actually pretty much exactly correct. And the period is pi. So if I just throw a little pi in here, then now you have a perfectly accurate graph. And anyway, the answer is definitely that it does not exist. Questions? Laura?
Would it be multiplied it by x squared over x squared? Wouldn't it then be equal to like 1 times x squared? Is that good to infinity?
This is x goes to infinity. So it's only what is x
What?
It says x approaches 0, not x approaches infinity.
Yeah. Yeah, don't fall for the trick. Sine x, so what is the limit as x goes to, 5 of sine x over x? So it's 1, 1, 1. No, it's not 1. Right, got it? Yeah, this is 2. This is 1 only when we're taking limits x goes to 0, but this is not. Okay, but good thinking. Okay, number 4 is just more practice with absolute values. We're taking the limit as x approaches a plus of x minus a over x squared minus a squared. So just fact, since I'm approaching a from the right, x is bigger than a. And since x is bigger than a, absolute value of x minus a just is x minus a. Yup, because x minus a is positive in this case. And therefore, we can simply write this, we can rewrite absolute value of x minus a as just x minus a. It cancels, bam, the answer is 1 over 2a. Cool? Whereas, by contrast, number 5, now I'm taking, this is basically the same problem, and now I'm taking the limit as x approaches a from the left. Well, since x is approaching a from the left, the absolute value of x minus a is negative x minus a when x is less than a, which it is in this case. So therefore, this expression just turns into negative x minus a, and those cancel, so we get negative 1 over x plus a, and that's just negative 1 over 2a. Are you guys cool with this? It's really not that hard, but I don't know. Number 6, Let's see what happened in number 6. This person did it this way, where you basically just use the binomial theorem, expand the whole thing out, and turns out to be 6. I have no comments about that. Cool. The other way you could do it, there's a kind of a fancy way you could do it with the difference of squares and difference of cubes and stuff. I don't know, did anyone try that?
Yeah.
Yeah, did it work?
Yeah.
Did you get 6?
Yeah.
Okay, cool. Alright, number 7. Limit as x approaches negative a half of the floor of 3x. Well, when you plug in negative half, you just get negative 3x, and the floor of that's just negative 2. So there's really not a lot going on in this problem. Number 8. We're taking the limit as x goes to infinity of 3x plus 4 over root 2x squared minus 5. And yeah, since x is approaching infinity, x is positive, so we divide the top and bottom by x, and we get 3 on the top. Put the 1 over x back in jail, so this becomes 3 over root 2. This is excellent. Number 9, pretty much, I have no comments to make. This is exactly what I would do in this situation. Turn the radicals into one big radical and then treat it like a rational function. It turns into be basically root 1/9, so it's just 1/3. 10 was a problem, just like we had on the quiz, except Eob, did you do this one? Yeah, Eob did it the weird Eob way, which is really cool and awesome that he just got invented this year. And copyright pending. The answer turns out to be 3/2. Is that what you guys got? Doing it the normal way?
Yeah.
Okay, cool. By the way, Eob, someone tried to do it your way on the quiz and just like screwed up and got lost. So they, it's your fault. You've led them astray. Was that you? That was you, right? I don't remember.
I did it both ways.
Oh, you did it both ways?
I got them both.
But you got them both wrong. Alright, okay, number 11 is another problem that was kind of like the problem on the quiz. I have no comments. I feel like we're experts at this now. 5/4? Yeah, good. Oh, this one gets kind of exciting. The limit as x goes to infinity of x squared sine 1 over x. Yikes. Who did this one? Yeah, Rohan. So, first off, Rohan says, okay, first of all, what's one thing that you might try, you might consider trying? Graphing.
Kind of. Or do you know that?
Given that this is the product of two functions, you might try to split it up, right? So if you try to split it up, this would be the limit as x goes to infinity of x squared times the limit as x goes to infinity of sine 1 over x. What is the limit as x goes to infinity of x squared? Count them like up. What's the limit as x goes to infinity of x squared? This is just clearly infinity. And this one, Calvin?
That would be 0?
Yeah. If I'm taking the sine of something that's tinier and tinier, then that's pretty much getting close to 0. So, wah, wah, wah. This is a good, bad idea. It's a good idea, but it's a bad idea. So we have to try something a little bit more sophisticated. How many of you figured this out, by the way? Like half? Less? Third? 2/3? Okay, so what Rohan says is, let's do a limit switchy. I will define a new variable y to be 1 over x, and the rationale here is that that there's only really one limit that I know involving x and sine x, and that's the limit as x is going to 0 of sine x over x, that is 1. So, given that that's the only thing I really know, but this limit's at infinity, perhaps what I can do is kind of like swap things around, right? So if I rewrite, if I define y to be 1 over x, then this becomes, and the other thing to observe, of course, is that as x goes to infinity, y goes to 0. And thus, that justifies what Rohan did here, which is to rewrite this limit in terms of a different variable. He replaces x squared with 1 over y squared, and he replaces sine 1 over x with sine y, and changes the limit as y goes to 0. And now we can freely split this up, and this limit goes to 1, this limit goes to infinity. Do you guys see what's going on here? I think that's kind of a hard problem. Okay, so this actually settles a kind of mystery of what this function f of x equals x squared sine 1 over x looks like. This question was, you got a review packet, right?
Oh, yeah.
This question, he has to go run.
He lost his quiz here.
Oh, okay, I don't know, whatever.
I'll talk
So, we'll divide up the points among the other students. Alright, so x squared sine 1 over x. This is a function which we mentioned. We had thoughts that said that we were going to graph this, right? This came up on the squeeze theorem day, I think. When we talked about the squeeze theorem, we said, well, this function is going to have a parabolic envelope. And also, what else is there to say about this function? It is odd or even?
Odd.
It is odd. And now I know, what I didn't know before, but what I now know is that the limit is infinity. Not only is the limit infinity, can someone say something actually even deeper about what this function looks like? What does this function look like as x goes to infinity?
It doesn't keep that.
It looks like y equals x.
It looks like y equals x, says Buses. Yeah, I agree. If you kind of look over here at, let's see, if you look back over here at Rohan's work, he got it down to this point for us, right? And then at this point, we can kind of split these limits up into the limit as y goes to 0 plus of sine y over y times the limit as y goes to 0 plus of 1 over y. Well, which is really just kind of like x, right? It might as well be x. Yeah, so it's sort of like this one is just going to 1, that one's looking more and more like 1, and this one is looking more and more like, if I kind of convert it back or whatever, I guess is what I'm really doing, right? Converting this back to the limit as x goes to infinity of x. So this is looking a lot like 1 times x. Does that make sense? Yeah. So, actually, there is a slant asymptote with this function of y equals x. And so when it comes to making the final graph, it's going to be kind of up here somewhere, and then it's going to kind of come down, and then remember towards the origin it starts going crazy, but it's crazy with a kind of constrained amplitude, and it's odd, so eventually, so it's going to look something like that. If anyone would like to calculate a graph and confirm how crappy my picture is, you may do so, but that's roughly the important points. All right, how are we feeling about all this? Good, that's 1 thumbs up out of 20. The rest of you are just staring at me blankly. All right, good. Other things. There's some homework. How'd the homework go?
Right.
Mateo, are you bored? You tired? I'm sorry, Mateo.
Can we do like
We're going to do some of these problems.
107?
Let's see. Can I get a new purple out of the cabinet, please? So, and then can you also raise the boards? So, there were some problems about the intermediate value theorem. Should we talk about that? Like 84. Let's do 84.
I didn't really like.
84 said, actually this is not that hard, but this is the class where, I think this might have been the class where we didn't really talk about this too much, we just like did it and kind of quickly moved on. F of x equals x cubed plus 3x minus 2, and this is on the interval 0, 1. Okay, and the directions were, explain why the function has a 0 on the given interval. And when they say explain, we're going to over-interpret that as like, prove that the function has a 0 on the given interval. All right, so why does it? Loosely speaking. Yeah.
Well, f of 0 is -2, f of 1 is 2. So between that, somewhere has to pass through 0 because it's a regular cubic.
Yeah. What do we call that theorem?
Intermediate value here.
It's the intermediate value theorem, yeah.
Okay.
So basically, this has to have a root on this interval because of the intermediate value theorem. Yeah, and so let's talk about this. What are the what actually must be true in order for me to be able to apply the intermediate value theorem at all? So.
That must be continuous.
Yeah, it must be continuous, and it just is because it's a polynomial, right? So you just gotta kind of gotta write something like f is continuous everywhere. something like this, because it's a polynomial. I'll take that as an answer. We sort of have a theorem that polynomials are continuous everywhere. But actually, that it's continuous everywhere is not my main concern. My main concern is that f is continuous specifically on the interval 0, 1. All right. So it's continuous on the interval 0, 1, and then we'll do what Yael said, which is to just try to see what f is doing at the endpoints. When I plug in 0, I get -2, and when I plug in 1, I get 2. Okay, so intuitively speaking, I have this sort of picture. I plug in 0, I get -2. I plug in 1, I get 2. And now my job is, can I get the red marker? My job is to suggest a y value in between 2 and -2 and 2, and one y value is 0. And if I suggest a number, that number is 0 in between 2 and -2, then it must be true since this function is continuous that it crosses there, right? So we have to say that, and the key points are, so how do we say that? Well, we have to suggest a number 0, and we have to suggest a number 0, which is between -2 and 2. And -2 is the value of f at the left endpoint of the interval, and 2 is the value of f at the right endpoint of the interval. So there are like two key statements here that need to be on your paper. One is that this function is continuous on the interval 0, 1, and 2, you need to suggest a particular y value, and the y value that we're suggested in this case is 0, which lies between f of 0 and f of 1. Is everyone with me? It's like not that hard. All right, once we have done this, then we can state authoritatively, so by the intermediate value theorem, someone finish off the sentence. Calvin, do your homework? You're looking like depressed, like how students look when they don't do their homework and they're just like consumed with just like guilt and. Calvin, let's try to participate. So by the intermediate value theorem, what? What does the intermediate value theorem say?
Intermediate value theorem says that if you have a negative number and a positive number.
No, that says more than that. Even 10. Finish off the sentence in a formal kind of manner. So by the intermediate value theorem, I've suggested a y value 0, which is in between f of 0 and f of 1. So what must be true?
So there must be, for at least one value of there exists a like f of there exists an f of like x that for at least one x value that lies between 0 and 1.
Yeah, usually called C. That's just kind of what we do, right? So there exists a C such that what?
Such that f of c is 0.
Okay, yeah, pretty much. Okay, yeah. There exists a C, which is, okay. There exists a C on the interval AB, or no, in this case the interval is 0, 1. There exists a C on the interval 0, 1, such that such that f of C is 0. Okay, done. Are we cool? That's not that hard. All right, just like quickly do one more. So 94 is basically the same. We're gonna do 107 and just. You want me to skip 94?
Yes.
Wait, what
Okay.
the answer for that?
We skipped 94. Let's go to 107. 107, very exciting. This is the mountain problem.
Yeah, I was like, what?
It has a name, in fact. It is called Deja Vu is the name of the problem.
What?
So when you start naming your word problems, you know things are getting serious. All right. Here is the story. We will read aloud. Classic calculus problem going on here, Eric. At 8 a.m. on Saturday, a man begins running up the side of a mountain to his weekend campsite. On Sunday morning at 8 a.m., he runs back down the mountain. It takes him 20 minutes to run up, but only 10 minutes to run down. At some point on the way down, he realizes that he passed the same place at exactly the same time on Saturday. Prove that he is correct. Yikes. Okay. Let's do it. Let's make a picture first. We can kind of think about what's going on. Here is a mountain. Like, I don't know, mountain. This could be better.
I don't think you can run up that in 20 minutes.
So mountain. Alright, and
Wait,
You're terrible.
in the
He-
picture, it was more like, yeah.
this is great. I'm really proud of this map I've drawn. So what is happening? He is running up the mountain. He begins at 8 a.m. Saturday right here. So here he is, and let's like timestamp this picture. He is right here at 8 a.m. Saturday, and now he is going to run up the mountain. And it takes him 20 minutes only to get to the top. So small mountain, not much of a mountain. Kind of like, yeah. All right. So basically, he goes up, and then he is at the top at 8:20 a.m. Saturday. Then he spends more or less 24 hours up there, and then on the way back, then on Sunday he goes back down again. So he is also at this same spot at 8 a.m. Sunday, and then he runs back down, and he arrives back down at 8:10 Sunday. All right. So if we were going to draw kind of like his path up and down the mountain, it would be like, he goes up, and then rests, and then comes back down again, something like that. All right. Now, not so exciting. Now they say at some point on the way down, he realizes that he passed the same place at exactly the same time. In other words, it was like he had a watch on, right? He's like running up the mountain, and he sees, like a pretty flower, something. Yeah, it's a flower. Bush, purple bush.
Like a zombie hand.
He sees a pretty, what?
It's like a zombie hand coming out of it.
Whoa. He sees a zombie, and he looks at sees a dead zombie? No, I don't know. A zombie that's not moving. Let's just let's go back to flower. He sees a flower, and he looks, or maybe it's like 8:05 or something like that. He sees a flower, he's like, oh, that's interesting. Let me just take a picture on maybe he takes out his phone. Yeah, that's good. Takes out a picture, he goes to take a picture of the flower, and he looks on his phone, and he sees that it's exactly, 8:00 something. Okay? And then, according to the story, on the way back down again, he sees that exact same flower, but now maybe it's like looking bloomed or something, or I don't know, the zombie is lost. I don't know. He sees the exact same object, and he looks back at his watch to take another picture, or back at his phone, and it's the exact same time. By exact same time, you mean 24 hours later, of course, right? Okay. Prove that in fact must happen. Prove that there must exist a point along his course in which he was at the exact same spot at the exact same time he was the previous day. Okay, talk to me. Mateo.
Special question. Do we get
Yes.
to assume that he's just moving at a constant speed as he goes up?
We should not we should not assume that he's moving at a constant speed. No, definitely not.
We should draw the graphs.
We should draw what graphs?
The ones that it says in the hint.
The ones that it says, okay, yeah. So, we could just pretend that we're really smart, or we could recognize that there was a hint given in the text, and the hint is extreme. The hint pretty much tells you exactly what to do, to the point where, like, raise your hand if you got this problem. Okay, 1, 2, 3, 4, 5, 6. If you didn't get it,
Maybe I didn't see what
the hint was right there. The hint tells you literally, like, do the following. Okay, the hint says, let S of t and R of t be the position functions for the runs up and down the mountain. And so, well, okay, let's just do that. Let S of t be the up the mountain function, and let R of t be the down the mountain function. So, what do these functions look like? Well, we can kind of sketch them. We can put time over here on the x-axis. And I guess this is going to be like distance or height or something. I guess height. This is height up here on the y-axis. Okay, so what is my height above the ground? And let's let 0 be 8 a.m. So here we are. All right, so where am I at 8 a.m.? I'm at the bottom of the mountain on the way up, right?
Yes.
And then how long does it take me to get to the top?
20 minutes.
20 minutes. So over here, we'll label our time in minutes, and at time 20, I'm pretty much there. Where am I? I'm at the top of the mountain. Let's say that the mountain is 1 mountain unit high. Just keep our numbers simple. So all I can say for sure about this function is that it looks, something like that, right? Those are the only 2 points I know. That's the go up the mountain function. Alright, what's the go down the mountain function? What does that look like? What are the 2 points? Yeah, at 8 a.m. Now this time I'm up here at 1 and I'm back down again by 10. I'm like back down, right? Yeah, and then I'm just staying here. I'm like we're down the mountain. So I don't know. It looks my going down the mountain looks kind of something like that. Everybody cool? All right. How does this actually help me prove that I am at somewhere at the same exact time? Yeah, Al.
So at 8 a.m. in the first graph, he's lower than he's at 0.
Yeah.
And at 8 a.m. on the second graph, he's at 1.
Okay.
And at 8:10 on the first graph, he's somewhere between 0 and 1.
Okay.
But at 8:10 on the second one, he's at the bottom.
Okay.
So in the first one, it's like he starts out lower and then ends up high.
Yep.
But the first one starts out being smaller than the second one, and
I
then
agree.
in the end, it's bigger than the second one.
Yeah. Yeah. So what?
So therefore they cross.
Oh. Okay. She says that these graphs must cross. This is okay. So I basically agree with you, but why? Why do they have to cross?
Well, if one starts out smaller and then becomes bigger than the other, which started out.
Yeah, I'm not convinced. Why?
Okay, so one of them, graph A starts out smaller than graph B. And
Yeah, I hear what
graph
you're saying.
bigger
If
than-
we try to draw the down function like up here, then it must look like this, right? So it certainly seems as if they probably cross.
He
Yeah.
never jumps on.
Yeah, there's probably like a word you should be saying now. Yeah, Rohan. Yeah, that's right. Yeah, continuity is going to kind of play some sort of role here, right? Because if this function's not continuous, then I don't see any reason why they should have to cross at all. Right? So that's sort of what's making this problem sort of interesting. Is continuity is involved in this, yeah. So I'll give you that. The functions are continuous because I mean, the guy's not doing any kind of quantum hike. This is just like a simple. This is just a simple walk up and down a mountain. So if these two, so suppose these two functions are continuous, prove to me that the curves must therefore intersect. I don't know, anyone.
I think people are reading.
Yeah, other people are raising their hand. Yeah, Emma.
So, I mean, you can use like the definition of like, because continuity means like, wait, never mind.
Does everyone see what's going on here? We're trying to, common sense says that the curves do intersect somewhere. And wherever they intersect, that is going to be a point at which, at the exact same time, they were in the exact same spot, right? So all we have to do is we have to prove that these two functions intersect. It certainly feels like they should intersect somewhere, because that's what continuous functions do, they don't jump around. But actually proving that they intersect using properties of continuity is like not obvious what to do. Except there was a hint, so it kind of is obvious. Yeah, Buses.
So if we follow the hint, we know
Yeah,
that
we
can
just
make
do. So
half of
Buses is
two
getting
meters.
frustrated. He's saying, this is fun conversation and all, but actually there's a hint given, and the hint pretty much tells you exactly what to do. And so we could struggle with this for a long, without the hint, I'm not sure I would ever be able to solve this problem. Because I certainly feel that they intersect, but something that's so obvious that they intersect is like, what are you gonna do? You want to do some non-hint way?
Yeah.
Yeah, what's that?
So by the intermediate value theorem,
Yeah.
both of those lines have to go through like every single point
Yeah.
in between the bottom and the top.
Uh-huh.
So if they both go through every single point, then they like have to intersect at like some point.
Okay. I love this answer because it's totally wrong. Let's. I think, or maybe not totally wrong, but not quite. So it sounds like what you're doing is good enough. Can I get the green marker so I can show you why this doesn't make any sense what you said? So Eob says, can I just apply the intermediate value theorem to this situation? Well, I certainly can pick some y value k, and I know by the intermediate value theorem that without writing out all the stuff, I know that there must be some point c where this s of c, or this s function is precisely k. Sounds good, right?
Yeah.
And applying k to the other function, I can also claim that there is definitely going to be a point where this other function has value k, let's call it at time d. But that's not what this problem is asking for. This problem is not saying show that there's some time c and some time d at which this function at which we are k units high up the mountain.
No, wait,
It's-
isn't it saying like what value of like just what value of function equal k like
Right?
Yeah.
At time
Yeah, where
c,
C and
there
zero
must be some time c at which this function is in which I'm exactly k units high up the mountain. And there must be some time d by the intermediate value theorem at which I am k units high above the mountain. But there's nothing that says that c and d have to be the same, right? What I'm trying to show is that that they must be at the same height at the same time. Okay, Buses, what do we do?
Okay, so we set f of t to be s of t minus r of t.
Yes, this is a brilliant move, and the reason why I'm spending so much time on this one like silly stupid mountain problem is because this actually exhibits a mathematical technique which we're going to use over and over again in this class, especially at one key moment, and that is instead of showing that two things are equal, like Yael got stuck trying to show that these two functions are equal somewhere. That's kind of hard. What's much easier, and they give you a hint in the book and tell you exactly what to do, what's much easier is to define a new function. Arun, are we still in frame? Mm-hmm. To define a new function, which is the difference of those two functions. And instead of trying to show that there is a point where these two functions have the same value, instead we will simply try to show that this function is 0 somewhere. And that's just like a thing that we're really good at, right? Showing where finding where functions are 0. Okay, so let's do it. If we define this new function f to be the difference of these two, then like, I don't know, what is f of 0, for example? Eric? -1, yeah, it's s of 0 minus r of 0. S of 0 is 0 and r of 0 is 1, so this is -1. Does everyone agree? And what is f of 20? Yeah, that's s of 20 minus r of 20. S of 20 is 1, and then s of 1 is 1. Okay, so now I can make a sketch kind of this f function, and here is what f looks like. At time 0 it's -1, and at time 20 it's at 1. And since this f function is a sum, or it's actually a difference of two continuous functions, then it must also be continuous. So everyone kind of see what's going on here? Basically now what we do is we apply the intermediate value theorem to f. So f is continuous on the interval 0 to 20, and that's one key step. And then the other key step is suggesting a y value, and here the y value we suggest is 0. So 0 is some y value between f of 20 and f of 0. F of 0 is -1 and f of 20 is 1. So, is this making sense? Now basically we apply the intermediate value theorem. So we apply intermediate value theorem to